Okay, so let's just get started. So, hello everyone. Today I'll be reviewing the 2023 F equals MA exam. Um, okay, so let's just get started with number one. So number one says there's a bead on a circular hoop with radius 2 meters. Right? And it travels counterclockwise for 10 seconds and completes 2.25 rotations. So it'll start here and it'll complete 2.25 rotations counterclockwise, like so, until it ends here. And this takes 10 seconds. So we want the average speed and the direction of its average velocity. Okay, so how will we do this problem? Well, first of all, let's try to find the average speed. So to do this, we can just use the definition of speed. Speed is the distance divided by the time. So we know that the time is 10 seconds, but what is the distance? Well, it completes 2.25 rotations, and each rotation, it will travel 4 pi because that's the circumference of our circle. So this means that the total distance traveled is 9 pi. All right, so now that we know our distance, we can find that our average velocity is just 9 pi over 10 meters per second. Okay. Now, what about the average velocity? Well, to find the average velocity, we have to find its displacement and then divide by time. That's the definition of average velocity. So starts out over here and it'll end up over here. So its displacement will then be this vector from the start to the end point. And when we divide that by time, the direction won't change. So in the direction of the final velocity will just be southeast. So the answer then is average speed is 9 pi over 10 meters per second. And the direction of the average velocity is down and to the right. Okay. And so that's number one. Feel free to stop me if you have any questions. And with that, let's move on to number two. Okay, so number two, we have an ideal pendulum here. And it's released from rest and it travels, it's not exactly, so it falls and it's not exactly vertical, but let me try to draw this better. So it'll fall like so. And then at this point over here, we want the direction of the acceleration. So how do we do this question? Well, let's draw a free body diagram. So right here's our point, and here's the string that's holding it up. Okay, so this is a pendulum here. And what are the forces acting on this mass? Well, there are two real forces acting on it, which are gravity here and tension from the string. Okay, so the answer is the sum of these two forces. However, there's also a condition that the mass has to be accelerating inwards. Now, why is this the case? Well, this is just because it's traveling in circular motion. So there's, in order for it to keep turning and keep changing its velocity, it has to have a centripetal acceleration equal to v squared over r times m. So it has to have this centripetal acceleration, which means that its radial net force must be pointed inwards. All right. So what do we have here then? We're going to have some tension which pulls it inwards enough so that the net force is mv squared over r radially inwards, and then we have the gravity. And then when we take the vector sum here, we should get a force that is both radially in, and also it should be perpendicular. There should be a component perpendicular to the string, because there's a component of gravity here that's perpendicular to the string, and there's nothing that can cancel it out. So it should be also accelerating downwards. So the final answer here is answer choice B, which is the only choice that matches our description. All right, cool. If any of you have questions, feel free to ask. Otherwise, I will continue on to question 3. All right. So let's do question 3. We have a soccer ball, which is being kicked up a hill. And what its trajectory looks like is something like this. And then when it reaches the top, the problem says that it just lands here and begins rolling horizontally. So we want to graph the vertical velocity over time. That's what the problem wants us to do. Okay, so what should the graph look like? Well, initially it's traveling up. It has some vertical velocity. So it should start out like somewhere here. And then as it travels, it should, the vertical velocity should decrease linearly because there's a constant acceleration due to gravity. But at this point here, it bounces up and it again has some vertical velocity. So what should happen here is as it bounces, there's a discontinuity and the vertical velocity kind of reverses itself because that's what happens when it bounces. And then it should go down again because now it's again accelerating due to gravity. And then it bounces again. Oh, there's only 3 bounces here, actually. Is that right? There's only 2 bounces here. So I guess it'll look more like this. But anyways, after it bounces again, it'll do the same thing until it finally reaches the top where its final vertical velocity is just 0 because the problem says it's rolling horizontally. And this graph best matches graph E. And so we're done. Okay, any questions? Okay, let's continue. Let's go to number 4. So what number 4 is asking is you have a plane here. It's inclined at an angle theta, and it has some height h. And you're pushing a box of mass m up the ramp. So a person's dragging the box very slowly up the plane, and that person applies a force parallel to the plane. So if this is the box here, the person will apply a force parallel to the plane. And there's also a coefficient of friction that's given to you, and it's mu k, the kinetic friction. So we want to find from the bottom to the top. So as the person drags the box from the bottom to the top, we want to find how much work is done by the person. Okay, so how will we do this? Well, let's just consider the work, the definition of work, which is force times the displacement, or I guess the dot product of force and a small displacement. So first, let's try to find the force that the person applies. So the person's dragging up this box very slowly. And that means that the box is just going at a very slow, constant rate. Right, so the net force on it must be 0 because it experiences no acceleration. So over here we have our applied force, and we also have gravity, normal force, and friction. So these will be the forces that act on our box. Okay. So now let's try to find some of these forces. We know that the acceleration is 0, so we have to balance out all these forces. We know that gravity is going to be mg. And immediately we can balance forces in the vertical direction. So in the vertical direction, gravity has a component of mg cosine theta, and it's downwards. If we make this our x-axis and this our y-axis. So gravity is mg cosine theta downwards, and it has to be balanced by normal force. So then we can just get the normal force immediately from this. And then we also can now balance forces in the horizontal direction, because now we can find friction by the definition of coefficient of friction. The friction is just mu times the normal force. So this is mu mg cosine theta. Okay, so now balancing forces in the horizontal direction, we'll get that the applied force minus the friction force equals 0, which means that the applied force is going to be equal to the force of friction, or mu k mg cosine theta. Okay. Now we found our applied force, so now we just have to, oh wait, sorry. There's also a component of gravity in the horizontal direction. Sorry about that. So there's our applied force minus the friction force minus our Fg cosine theta, sine theta. Okay, this is the component of gravity in the horizontal direction. So this now is equal to 0. And then we can find our applied force, which is actually mu k mg cosine theta plus mg sine theta. Okay. Now let's continue. We found our applied force. Now we just need to find the displacement. Well, finding the displacement is not too hard, because we know that this height, we know the height of the ramp, and we know the angle. So the displacement is just this distance. And we can use geometry to get that the displacement is h over sine theta. So now the work done is the force mu k mg cosine theta plus mg sine theta times the displacement h over sine theta. And if we simplify this a little bit, this just becomes mgh times 1 plus mu k cotangent theta. And so this is our answer. Okay. Do you have any questions? Now I will continue to question 5. Okay. So in question 5, we're given a system of pulleys. And we have just two pulleys here. And they're attached to 3 blocks like so. two of the blocks have mass m, and the third block has mass 3m. Okay. And what we want to do is just find the acceleration of each of these masses. So how do we approach this problem? Well, this is known more generally as an Atwood machine, basically just a system of pulleys. And normally the solution to these just involves drawing force diagrams for each mass, and then you should get a system of equations using F equals ma and also conservation of string. So let's first look at the conservation of string concept. So the idea behind that is if we have a pulley or pulleys here, and let's say we move our mass up by a distance x. Okay. Well, for this string to remain the same length, that means that our mass of 3m must move down by a length of x. And also that means that this mass must move up by a string must move up by a length of x in order for this string to stay the same length, because this end also moves down by a length of x. Okay, but what does this mean? This basically means that the acceleration of each of these mass m's upwards is equal to the downwards acceleration of the 3m mass. Okay. So now we can use our force equations. So let's draw a force diagram on our mass m first. So the two forces that act on it are gravity and tension. All right, simple enough. Now, if we move to our mass 3m, it's similar. There's just gravity, and in this case, there will be two forces of tension because there are two strings attached to it. So there's one from each string. Can you use symmetry? This is equivalent to an Atwood machine with 2m and 3m. Let me think about that. I think so. I think you can also use symmetry and have 2m and 3m. I think the equations will work out to be the same. Yeah, that's a good idea. So if we just continue with our F equals ma equations for the mass m, what's the net force on it? Well, there's t upwards and mg downwards, and this is equal to ma. Okay, and now for our mass 3m, there's going to be 2t upwards and 3 mg downwards. And remember that this mass is accelerating a downwards. So this has to be equal to -3 ma. So now remember what the question is asking for. We need to find acceleration of mass m. So this, we just want to find a. So with that in mind, let's just eliminate t. So we have 2t minus 2mg equals 2ma, and 2t minus 3mg equals -3ma. So now we can just subtract them to eliminate t. And we get that mg equals 5 ma, which means that a equals g over 5. And that is our answer. Okay. And like someone pointed out, you can also just make this equivalent to an outward machine with masses 2m and 3m, because like symmetry, all the forces will just combine and then they're effectively the same thing. So if you know the formula for this, you can also use that. Very cool. So any questions before I move on? If not, I will continue to question 6. Okay, this question is a bit tricky, so let me talk about it. First of all, we have a ball at the end of a rope, and it's being swung at 15 meters per second. Shoot, that's not the right arrow. Okay, just imagine it moving around as it's swinging in a circle, and it has speed 15 meters per second. Okay. And we know that the rope is length 0.5 meters. So what we want to do is we want to find this height here. So how will we approach the problem? Well, first we would want to find this angle theta here. And from there, we can find, so we want to find the height. And we know that the height is the length of the rope, L, times cosine theta. So the problem is equivalent to just finding what theta is. Okay. So now let's see what happens to the ball. It has two forces on it again. It has tension and it has gravity. And if we extend this angle is still theta. Do we have a question here?
Is there centripetal force?
Okay, so centripetal force, yes, it is a thing, but the terminology around this is quite weird. So what we call centripetal force is not actually a real force. What it is whenever our ball's moving in a circle, it has to be accelerating inwards. So it has to have a net force that's equal to mv squared over r. And this is what we call our centripetal force. And in this case, it will be provided by the tension in the string. Alternatively, what we can do is work in the rotating frame of the ball, in which case we'll have to add a fictitious centrifugal force, which has magnitude mv squared over r. But let me just do it the way I was originally going along with, which is to just solve it in the lab frame. Okay. So we're solving it in the lab frame. And since we know that it's moving in a circle, we need the sum of these two forces to go inwards and have a magnitude of mv squared over r. Okay. And what does this mean? Well, if we draw a triangle here, first of all, let's decompose t into its components. So we have t sine theta here and t cosine theta here. And then we also have gravity, of course, which is mg. Okay. So we know that t cosine theta has to be equal to mg, and that t sine theta has to be equal to mv squared over r. Okay, but what is r? R is not actually the length of the string, but r is this distance here. This is r, which is the length of the string times the sine of theta. So what this is mv squared over L sine theta. Okay, now we have these two equations which have two unknowns, and we want to solve for theta. So again, we want to eliminate t. So let's divide our equations. T sine theta over t cosine theta equals mv squared over L sine theta divided by mg. Okay, and then after simplifying, sine theta over cosine theta will be equal to v squared over sine theta lg. And now we cross multiply. So sine squared theta equals cosine theta times v squared over lg. And then from there, one way to do it is just make this 1 minus cosine squared theta equals cosine theta times v squared over lg. And then this is just a quadratic in cosine theta, and we can solve it for cosine theta, and then arc cosine it to get theta, and then plug it all back in. And that's the way I did it. The way the solutions does it is to use small angle approximations, which in this case, we can take this equation, and I think we can just use sine theta. Oh, wait. For smaller angle approximations, I think we'll have to redefine our theta. So if we had instead defined our theta to be this angle, which is 90 minus our original angle, then we would have gotten cosine squared theta is equal to sine theta times v squared over lg. And then from there, since theta is small, we can then use that sine theta is approximately theta and cosine theta is approximately 1. And then we will get that sine theta is approximately lg over v squared, and then continue as normal to find L cosine theta. And the answer you end up getting is that h equals 1.1 centimeters. Okay. Any questions? All right, then let's continue. Let's do number 7 now. So for number 7, we have 2 boxes that are stacked on top of a third box. And all 3 boxes have mass m. And they're sliding on a frictionless surface. And the bottom box is being pulled with a force F. And there's only one surface with friction, which is this surface between the leftmost block and the bottommost block. So this surface has friction. This surface has friction with coefficient of friction mu s. This surface here. But all other surfaces are frictionless. So what we're asked is, what is the minimum value of mu s such that these boxes don't slip with respect to each other? All right, so there are 2 ways that I know of that we can solve this problem. I'll go through the standard method first. So the standard way, whenever you see these problems, you can usually just draw some force diagrams to solve them. So this is the leftmost block. Let's draw a force diagram on that. So it has gravity and it has normal force. And in order for it to be pulled along with the other blocks, there has to be some friction in this direction. But there's also a normal force, let's call it N2, I guess, from the rightmost block, which also has to be pushed by normal force. So if we consider the rightmost block, there's gravity and normal force from the bottom block, but there's also a normal force from the leftmost block, and that's the only thing that can push it forwards. So there has to be a normal force in order for the blocks to not slide with respect to one another. Okay. And then for the bottom block, while you have gravity, as usual, you have the reaction forces from those 2 normal forces. And you also have the reaction, you have the applied force and the reaction force from this friction force. So these are action-reaction pairs. The normal forces, of course, also action-reaction pairs. So we can just use F equals ma on all 3 of our blocks. So if we do it on the bottom blocks, the bottom box, we have the applied force Fa minus the friction force equals ma. And then if we do it on the left box, we get that the friction force minus the normal force from the right block, it's equal to ma. And we have, if we do it on the rightmost box, we'll just have the normal force, that's the only thing accelerating it, should be equal to ma. And notice that all 3 of these a's are the same. This is because these boxes are all moving as a unit, right? Because if they're not sliding with respect to each other, then they have to be moving with the same position, same velocity, so they have to have the same acceleration. So now what we just want to find is the friction force. So you can notice that if we add all these equations together, we'll get something very nice, which is just that the applied force is 3 ma. So from there, we can get the acceleration to be the applied force over 3m. Okay, so now all we have to do is take this equation, plug in our A to get the friction. So we get our applied force minus the friction force equals ma, which is F over 3, which means that the friction force is 2F over 3. From there, we get the coefficient of static friction by the definition, which is just mu s equals the friction over the normal force, which is then 2F over 3. And the normal force here, it just balances out mg, so has to be mg. And so that's our answer. All right. Okay, so there is also a second way to do this problem, which is a bit nicer, in my opinion. How we do it here is we consider these 3 boxes as one system. So this collection of 3 boxes is equivalent to just one big box of 3m if you're looking at it from the outside. And this is because if they're not sliding, as I said, they have to be moving together. So they're equivalent to just one big box. And we know that the net external force on it is just F. So we can immediately get the acceleration, which is F over 3m. Then from there, we can consider this as 2 separate boxes now. So now we're looking at 2 systems. One of them has m, and then one of them is the 2 boxes on top, and they have mass 2m. So now, if we look at, okay, this box is accelerating a equals F over 3m, and this box is also accelerating a equals F over 3m. But the only horizontal force on this box here is friction. So then we can get the friction has to be ma, or in this case, 2m times F over 3m. This is our m, this is our a. So anyways, this is 2F over 3. So this is a faster way to get what our friction and our acceleration have to be. And then from there, you can just continue as normal. Okay, any questions? Let's continue to number 8. Oops. Okay, let's continue to number 8. So number 8's pretty simple. We just have 2 stars, alpha and beta, and they're orbiting around each other. And MA, the mass of A, has 10 times the mass of alpha, that is. Alpha has 10 times the mass of beta. So we want to find in the rest frame of the system, we want to find the ratio V alpha over V beta. Okay. And for this question, I'm assuming what they mean by the rest frame of the system to be the rest frame of the center of mass. So let's just say the center of mass is fixed here. Now, if the center of mass is at rest, then the center of mass velocity has to be equal to 0. Well, how do we find the center of mass velocity? It's actually quite easy. It's just m alpha times the velocity of alpha plus m beta times the velocity of beta. Oops. And then divided by the total mass m alpha plus m beta. And this has to be equal to 0 if it's the rest frame of the system. Okay. So we know that m alpha times v alpha equals negative m beta times v beta. But wait, we already know that the ratio of m alpha over m beta is 10. But we can rearrange this to get m alpha over m beta equals negative v beta over v alpha. So we can just get that v alpha over v beta is 1/10. And I just dropped the negative sign there because the question says speed. So absolute value of whatever we have. And so this is our answer. Okay. Now let's talk about question 9. Question 9 is a conceptual question. The question is, we have a helium balloon that is, oh, it's not floating yet. So we have a room that has air in it, of course. And then we have a helium balloon here. And it's released at the floor and it floats up to the ceiling. So what happens during this process is that the gravitational potential energy of the balloon has increased. So gravitational potential energy of the balloon has increased. But there's conservation of energy. So some other energy must have decreased. And the question is asking, what's the main contributor to the decrease in energy? Well, to do this, we're effectively, if you think about it, as the balloon goes from the bottom of the room to the top of the room, there's going to be, it's effectively transferring a parcel of air from the top of the room to the bottom of the room. So the answer here is that the energy is coming from the potential energy of the air inside of the room that's decreasing slightly. Do we have a question? Shouldn't the kinetic energy decrease because the balloon has to slow down as it reaches the ceiling? No, and the reason why is because initially the balloon is at rest, right? So it has no kinetic energy. So, and So how to explain this? Initially the balloon doesn't have any kinetic energy. And at the very end, it also doesn't have any kinetic energy because it's also at rest at the very end. So there was no total decrease in the kinetic energy of the balloon. Does that sort of make sense? Okay. And so as I was saying, the main contributor to this increase of energy in the balloon is just this parcel of air here moving down to the bottom of the room. And that's where the energy comes from. And if you think about it, it accounts for basically all of this energy because the balloon is rising very slowly, right? So very slowly. This implies that the density of the balloon is approximately equal to the density of air. So this volume of air is basically the same, almost the same mass as the balloon. Maybe it's slightly more, and that's where the balloon gets its extra velocity from. So as the balloon goes up by mgh, the air will fall down by the same height that the balloon rose up. So the potential energy of the air will also decrease by mgh. And so there's that accounts for basically all of the energy. Okay, do we have any more questions or can we continue? All right, let's continue. So question 10 says that uh an archer aims at a target. So here we have an archer. Okay, we have an archer and she's aiming at a target that is, target here, that is 100 meters away. Okay. And she shoots with a velocity 100 meters per second. And we want to find the angle theta such that she hits the center of the target here, which is basically at the same height as she fires the arrow. So this is just a standard kinematic sort of question. So all we have to do, say the angle is theta, right? We can write the equations of motion for both directions. So the x velocity initially is v times cosine theta, and it has no acceleration in the x direction. So that means that the x distance traveled is just v cosine theta times the time. In the y direction, the initial velocity is v sine theta, but we also have an acceleration of g downwards. So we have to subtract 1/2 gt squared. All right. And what happens at this target? Well, at this target, x equals 100 meters and y equals 0. So we'll have a system of equations to solve. So if we solve y equals 0, first of all, this just gives us v sine theta t minus half gt squared equals 0. If we solve this, we'll see that t equals 2v sine theta over g. Now we can plug this into our initial x equation, so v cosine theta times t, which is 2v sine theta over g times v cosine theta. And this is 2v squared sine theta cosine theta over g. And if you use trig identities, this is also equal to v squared sine 2 theta over g. And this is a very nice form for it to be in, because now we can just say v squared. So we know what v is, right? V is 100 meters per second. So 100 meters per second squared times the sine of 2 theta over our g, which is 10 meters per second squared. And we know the range, which is 100 meters. So now we can multiply and divide everything to get that the sine of 2 theta should be equal to 1/10. Which then means that our theta is just arc sine of 1/10 divided by 2. And so that's our answer. All right. Now let's move on to number 11. Number 11 actually uses the same formulas mostly as this question. So number 11, we also have a projectile. It's fired upwards, and it lands a distance h from its starting point. But we also know that its maximum height reached is also h. Okay. So first of all, let's try to use our work from the previous question. We get that after it reaches the ground, the x it travels is 2v squared sine theta cosine theta over g, and that's equal to h. Now, what's its maximum height? Well, we know that at its maximum height, the y velocity has to be equal to 0. Well, why is this? If it has a positive y velocity, then it'll continue going up. So its height will continue increasing, and that won't be our maximum height. But if it's going down, that means that its height's already decreasing. So the maximum height was some time in the past where it wasn't going down. So with this, let's try to find its maximum height. Well, its initial y velocity here is v sine theta. Its initial velocity is v sine theta, and it's accelerating downwards at a constant rate of g. So its y velocity is v sine theta minus gt. And if this is equal to 0, that means that t must be equal to v sine theta over g. So now we can bring our equation down here. We get that y v sine theta t minus half gt squared. And if you plug this t into this equation, you'll get v sine theta times v sine theta over g minus half g, and then v sine theta over g squared. And if you simplify this just becomes v squared sine squared theta over 2g. Okay, and this is also equal to h. So what does this tell us? These things are both equal to h, so they must be equal to each other. So we know that 2v squared sine theta cosine theta over g equals v squared sine squared theta over 2g. And if you do a little bit more algebra, this just means that tangent of theta should be equal to 4. Okay. And so now what? The question is asking us, what is the maximum height if it was thrown directly upwards? So for this, we'll set theta equals 90. So it's basically this was our max height equation, right? And our height, if we throw it directly upwards, is the same, but theta equals 90. So that just means sine theta is 1, so this becomes v squared over 2g. So we want to find v squared of over 2g. And we know that from here, we know that v squared sine squared theta over 2g is equal to h, which means that v squared over 2g is just h over sine squared theta. So now we can just use math. We know what theta is. So this will be, if we didn't want to use a calculator, we could just use trig identities. So we'll get that this thing is true. And then this is just h times 1 plus 1/4 squared, which is 17 over 16h. And that's our answer. Okay. Now, if we don't have any questions, let's go on to number 12. So what is number 12? In number 12, we have two strings connected to a block of mass m. So initially the tension is T1, but now we take scissors and cut this string here. So now there's no more string here, and then the tension in the diagonal string becomes T2 suddenly. So we want to compare the magnitudes of T1 and T2. So to do this, let's draw force diagrams. So in the first case, there's mg here, and there's tension from both these strings. And if we look at it in the vertical direction, let's say this angle is theta. If we look at it in the vertical direction, there's only two forces. There's T1 sine theta, that's the vertical component of T1. And there's also mg, and they have to balance each other out. Okay. Now, what about in this case? What happens after the string is cut? So let's call this theta again. There's going to be gravity and tension, but nothing else really. So in this case, if we do a bit of geometry, we should get that this angle is also theta, and that will be useful because what will happen here is that we have to balance forces perpendicular to our string. And the reason why is because if we accelerate towards the string will just become loose and then won't be any more tension. And if we accelerate away from the string, that'll be like trying to increase the string's length. But if it's like an ideal string, that can't happen. So it'll increase the tension to pull it back. So what all this means is just we're trying to balance forces along this direction of this, along the direction of the string. So that's fine. We have two forces in that direction. We have the component of gravity, which is mg times sine theta, and that should be equal to T2. All right. So now let's compare the magnitudes. So T1 equals mg over sine theta. And since sine theta is less than 1, we know that this is greater than mg. Meanwhile, T2 is mg sine theta. And since sine theta is less than 1, this has to be less than mg. So this gives us our final answer, T2 less than mg less than T1. All right. Now, let's go on to question 13. Okay. In question 13, we have a box that has some mass and it's sliding on some floor that has friction. So what happens is we're pulling it along with some force F, and we continuously increase the force. So it starts out with no force and then it increases slowly and slowly until either the box lifts off the floor or it starts sliding. So the question is, will it slide first or lift off the floor first? So let's look at what's happening here. First of all, what will cause it to slide? Well, if it slides, that just means that the horizontal component of our applied force is greater than the force of friction. And so that will cause it to slide. And remember that the force of friction is equal to mu times the normal force. So for it to start sliding, we have to have the force times cosine of whatever angle it's at has to be greater than mu times the normal force. Okay, but what's the condition for it to lift off the floor entirely? Well, in this case, what it means to lift off the floor just means that the floor is no longer pushing up against the block, right? So the block is just there. It's not supported by the floor anymore. So what this means is that the normal force on the block has to be equal to 0. Okay, so which one will happen first? Well, let's look again at what happens to the normal force. So as this force increases, as the applied force increases, it can almost balance out gravity. So what we have if we try to balance our forces is that the normal force plus the applied force times the sine of the angle equals gravity. So as this thing gets bigger, this thing can get smaller and smaller until it, so yes, so the normal force is continuously decreasing and the applied force is continuously increasing. So I think the idea here is, first of all, I'll tell you the answer, which is that it'll always slide first. And the reason why is because it can slide even if there is some normal force. But the only condition for it to lift off the ground is that if there's no normal force. And since the normal force is linearly decreasing, this basically means that it'll reach a small value before it reaches 0. Yeah, hopefully that makes some sense. So the answer is the box will slide first, always. Okay. Now, does anyone have any questions so far? Okay, then let me continue. So let's go to question 14. What question 14 is asking is you have this figure here. It sort of looks like this, kind of a reversed lambda. And it's made of these 3 rods, which all have the same length. So this one, and this one. They all have the same length and they have the same mass, and they all have uniform density. So what we want to find is, okay, so first of all, this thing sits on a table, right? So there's going to be normal force on its 2 legs. And what we want to find is what fraction of its weight rests on the left leg. So we want to find the normal force from the left leg and then divide it by the total weight. So how will we do this? The way I did it is to balance torque around the center of mass. So if we draw this out again, a bit bigger this time, where's the center of mass? Well, you can think of the center of mass of these 3 rods as the center of mass of something here that has 2m, because that accounts for these 2 rods. and then something here that has mass m that accounts for this rod. So the center of mass will be over here somewhere. The important thing about this is that the center of mass, let's call this distance here L. Yeah, let's call it L. The center of mass will be a distance of L over 6 to the right of this center here. And why is that? Well, that's just because this distance here is L over 2. And since this one is twice the mass of this one, the center of mass will be a third of the way from this one to this one. So a third of L over 2 will be L over 6 here. So now let's try balancing torques. So we have our shape here. And if we draw this, so this will be 5L over 6, and this will be 7L over 6. 6, not G. So if we balance torques, we'll have F and L and F and R. And we'll basically have that. First of all, we have to have force balance. So the sum of the two normal forces must be mg. But also we need to have torque balance. So 7L over 6 F and L plus 5L over 6 times F and R equals mg. So if we solve these equations, it's pretty easy to see that the solution of this is just, sorry, this is not the torque balance equation. I misspoke earlier. The torque balance equation is that 7L over 6 F and L is equal to 5L over 6 F and R. This is because the torque, okay, yeah, just the torque from this one equals the torque from this one in the other direction. So if you solve these two equations, you'll just get that F and L is 5/12 mg and F and R is 7/12 mg. In either way, yeah, in any case, the answer is it carries 5/12 of the weight. Okay, any questions? If not, let me move on to question 15. So let's talk a little bit about question 15. Ooh. So in question 15, we get a graph, which is the velocity curve of some galaxy. And what this is plotting is basically we have, let's say we have a galaxy over here, looks something like this. It's plotting the speed of some point that's r away from the center is going to have some speed, and some point another r away from the center is going to have some different speed. So it's plotting these speeds as a function of r. And the graph given looks a bit like this. And so what it's asking is what does the mass distribution of this galaxy look like, assuming it's spherically symmetric? So let's see. This is the it's the velocity orbiting. So for this question, we will use the orbital velocity formula. So where that comes from is, let's say you're orbiting some star at a radius r, and you're traveling with velocity v. So there's going to be force on you, that's gravity, gmm over r squared, and that has to provide your centripetal force, which is, it has to be equal to mv squared over r for you to stay in a circle. So what this gives is just v equals square root gm over r. Now let's look at what our graph is showing us here. Basically, in our graph, the velocity is pretty much constant throughout most of the graph. So this means that square root gm over r is constant. Okay. So g is our gravitational constant. That's always a constant, which means that m over r has to be a constant. So what will happen if you graph mass as a function of radius is that you'll get something similar to a straight line. So that is answer choice B, and that's what was originally accepted as the correct answer. However, there was this thing where answer choice D is also accepted, and the reason why is because right here, there's a little region where it's not constant initially. Initially it's rising. So what you would see in this region is a graph where m over r is increasing. So the slope of the graph is increasing initially. So if we graph what happens here, it's going to initially have be a little bit curved upwards, and then after that it'll be constant, which is also similar to what graph D looked like. So answer choice D is also accepted. Okay. Now, are there any questions? If not, I will continue, since we are a bit short on time here. So let's go to question 16. Question 16. So in question 16, we have a pendulum here. What happens is our pendulum here swings, but before it can swing to the other side, it hits the wall and then just bounces back. So, and it has an initial angle of theta 0, which is supposed to be small, but I drew it big here just so you can see it. And then it collides with the wall when it has an angle theta 0 over 2. So we want to find the period of the bead going this way, colliding and coming back. So we want to find the time between two collisions, basically. So first of all, let's think about what would happen if there was no wall. It'll just go back and forth. And for this, we can just use the classic equation t equals 2 pi square root L over G. Right. So this is the period if there was no wall. And we're given that L equals 10 meters. So this will be 2 pi root 10 meters over 10 meters per second squared. So the period is 2 pi here. Now, what happens when it collides with the wall? First of all, the motion after it collides with the wall is completely symmetric to the motion before it collides with the wall. So we can just ignore that and calculate the time it takes to collide. And then multiply it by 2 for the final answer. So now what do we do? We can express the angle of the pendulum as a function of time, right? And this is it's undergoing simple harmonic motion. So it's going to be sinusoidal. We know it's initially theta 0, and it varies sinusoidally like so. And this is just cosine of 1 times t, because we know that the period, first of all, if this is, let's just call it omega t for now. We know that the period is 2 pi seconds, right? So 2 pi over omega is 2 pi seconds. So then we'll just get that omega is 1 over seconds. Okay. So now, at what time will theta become negative theta 0 over 2? That just means that theta 0 cosine omega t equals theta 0 over 2 negative, which will happen when omega t is equal to negative 2 pi over 3. All right, so this will happen at t equals 2 pi over 3 seconds because omega is 1 over a second. Oops, no negative here. So it'll happen when omega is 2 pi over 3 seconds. And so remember that we were going to multiply by 2 to get our final answer of 4 pi over 3 seconds. Cool. With that, let's move on to question 17. Oops. Okay, question 17 is asking, so we have 3 pendulums. One of them is just a mass m. One of them is a thick rod, which also has mass m. And one of them is a rod of twice as long, but also mass m. So this distance here is L. This distance is also L, but this distance is 2L. So the question asks us to rate to rank the moments of inertia I1, I2, and I3 around their pivot points, respectively. So let's just calculate the moment of inertia of these things. So for the first one, I1, this is just simply ml squared, because it's just the mass that's L away from the pivot. For I2, this is just, you can use the formula for a uniform rod. And this formula will be 1/3 ml squared. And for this one, you can use the same formula actually. 1/3 m times 2l squared, which end up being 4/3 ml squared. And then from there, you can just see that this is the correct ranking. And that's our answer. Okay. Now let's move on to question 18. So in question 18, you have a tub full of water. And at the bottom of a tub of the tub, you have a bathroom scale. So we have three people, Alice, Bob, and Carol, which each have rocks that they want to measure. So they measure the weight of their rocks by putting it on the scale here. So first of all, Alice has her rock in an airtight bag, and this bag has no air inside it. So it's sealed completely and there's no air. Okay, Bob has a bag, the rock also inside of his bag, but it's filled with water. And Carol has the rock inside her bag, but her bag is filled with air. So we want to rank the weights that they've measured. So let's think about it for a bit. First of all, what's the weight that Alice measures? Well, the weight that Alice measures would be the normal force of the scale on the rock, right? So if we draw a force diagram, the rock has mg gravity downwards, and it has normal force from the scale, but it also has a buoyant force from the water. And by Archimedes' principle, this is equal to the density of the water times the volume displaced. All right, so the weight measured by Alice will just be equal to mg minus this buoyant force. Now let's look at what the weight Bob measures is. So Bob has the rock inside of a bag now. And the total weight of this bag is going to be mg plus the volume of the water in the bag times the density of the water times g, right? Because that water is going to add mass to the bag. However, this will also add some volume to the bag. So the force, the buoyant force, is then the density of water times the volume of the rock plus the volume of the water. So again, if we go back to Alice's, this is just mg minus the density of water times the volume of the rock, right? Because the volume of the rock is basically the volume displaced. But now if we go here, we'll get that the weight of Bob's rock is mg plus the volume of water times the density of water times g. But then, oh, hold on. There's a g here also that I kind of forgot. Okay, yeah. So the buoyant force is equal to the weight of the water displaced. So this is the mass of the water displaced and multiply by g to get the weight. Okay, so we're going to subtract the buoyant force here like normal, which will be the density of water times the volume of the rock times g. There's a g here, minus the density of water times the volume of water times g. Okay, but these two terms here will cancel out. And so we'll get mg minus rho water times volume rock times g. So this is actually the same. We get WA equals weight B. Now what about Carol's weight? Well, it's going to be the same thing, except instead of the density of water here, it's going to be the density of air. So mg plus bw times the density of air times g minus rho w volume of the rock times g minus rho w volume of the air times g. Okay, so this is mg minus rho w times the volume of the rock times g, but then it's also, we're also subtracting what is this? Rho water volume air times g minus rho air times volume of air times g. So we're subtracting this quantity. This quantity is definitely greater than 0 because, okay, we can factor out volume of air times g here. Oops, it's not what I meant to do. We can factor out the volume of air times g. So we get this. And now we can see this is definitely positive because air is denser than water. Shoot. Okay. So that then means that the weight that Carol measures is less than the weight that Alice measures, which is equal to the weight that Bob measures. And this is our answer. Okay. If no one has questions, let's move on to question 19. So what's going on in question 19? A student sets up a pendulum and it has length equal to 0.50 plus minus 0.01 meters. And the student observes the period to be equal to 1.4 plus minus 0.1 times seconds. And so the student uses this data to compute G, which is 10.1. So the student gets 10.1 meters per second squared, but there's going to be some uncertainty delta G. So we want to find delta G. how much uncertainty is in his measurement for gravity. So first of all, to just review the period of a pendulum, this is the formula for it. And so what we're going to have here is t squared equals 4 pi squared L over G, which means that the formula should have used, the formula the student should have used to get G is 4 pi squared L over T squared. Okay, so now we want to find what the uncertainty in G is, and we can use the ratio, the formula for uncertainty in its most general form is, oops. Delta x times partial G partial x squared. So for each variable x that delta G depends on, we're going to add up their uncertainties and then add up the squares of their uncertainties and square root the whole thing. And this is just a result of linearity of variance. So if you've taken statistics, this is just linearity of variance. So what does this mean for us? Well, it just means that it's the uncertainty in L times whatever 4 pi squared over T squared, because an uncertainty in L will increase G by 4 pi squared over T squared times whatever that amount of L is. And so that's our uncertainty in L. And then we can do the same thing for uncertainty in T times, we'll get negative 8 pi squared L over T cubed, I'm pretty sure. And so now we have all of these numbers. So all we have to do is plug stuff in. And after we do that, we should get 1.4 meters per second squared. Quite a big uncertainty for calculating G. Okay. With that, let's move on to question 20. So in this question, we have a pendulum again, and it's oscillating back and forth, and we want to plot its x velocity versus its y velocity. And these are axes, by the way. The question says that the x-axis is along this way. It's one of the directions where it oscillates. And the y-axis is vertically upwards. Okay. So how will we do this question? Well, okay, first of all, let me tell you what the question was asking. The question is asking, we want to plot Vy versus Vx. So the question gives us a bunch of graphs that are Vx of t and Vy of t, and these will be parametric curves. And it gives us a bunch of choices, so these are the choices here. Okay, so these are the choices. And we want which one could be a graph of Vx versus Vy. So one fast way of doing this should just be to notice that over the course of an oscillation, like initially it's at rest, so it'll start at the origin. So first of all, graph has to pass through the origin. We can eliminate this choice and this choice. And then it'll go to some point where at the bottom, it's moving in the x direction and its y velocity is 0. So there has to be some point on the x-axis where Vx is not equal to 0, but Vy equals to 0. And actually already that eliminates our other two choices. So we can just choose this choice, which was choice C. And basically that's how I would go around doing this in the contest, just see special points, see if they're on the graph or not. Okay. Now, let's go on to number 21. So what is 21 asking? We have a smooth ring of radius r. And we have, the ring has mass m. And we also have another mass, which also has mass m here. So initially, this mass m is given a velocity v. And so we want to find how much time it takes before it'll travel one full like rotation around the ring. And I guess this problem's a bit tricky because as the mass moves, it'll push on the ring, so the ring will move along with it. And there's one way I solved it, which is to work in the center of mass frame. So if you like just draw the center of mass frame. So first of all, the center of mass is over here, right? And in the center of mass frame, this mass will be moving v over 2 to the right, and the ring will be moving v over 2 to the left. And if you think about it, what they have to do in this frame is they'll just move around in a circle like so. So this mass will move that way, this mass will move that way, and they'll go around in a circle. So the time this will take, the length of the circle, first of all, is just 2 pi times the radius, which is r over 2, and then the velocity is v over 2. So this distance is 2 pi, the time taken is 2 pi r over v. That's our answer. Alternatively, the solution given by AAPT is that whenever this ring's pushing whenever the mass pushes on the ring, it's always going to be an elastic collision. And whenever there's an elastic collision, the relative velocity of the two masses stays the same. So what this means is that this mass always has a velocity of v relative to the ring. So as it goes around this way in the ring's frame, it travels 2 pi r and its velocity is v. We get the same answer. So that's our answer. Now let's go on. We're a bit short on time, so let's just go on to number 22. in number 22, what we have here is 3 different spring configurations. So one of them's in series, one of them's connected to a pulley, and one of them is in parallel. So we have 2 springs. In each case, there are 2 springs, the one with K1 and one with K2. And we want to compare their effective spring constants. So let's look at the first case. If we extend this end here by a distance x, then each one of these springs will be extended by x. So the end will have 1 force of K1 x pulling on it and 1 force of K2 x pulling on it. So the effective force is K1x plus K2x. And this should be the effective spring constant times the displacement. So this just means that the effective spring constant is the sum of the 2 spring constants. Now, we can do a similar thing for these 2. Let me do the third one first, actually. This is a more standard configuration. So we have K1 here and K2 here. And if we extend this distance, distance x, let's say K1 is extended by x1, K2 is extended by x2. So we have to have 2 conditions. First of all, x1 plus x2 has to be equal to x. This is kind of obvious. It's just like the 2 extensions have to add up to the total extension. But we also have to balance forces on this point, which is the point connecting the springs. And this is because otherwise, this point connecting the springs will shift around and that'll change the spring forces. So we need K1x1 to be equal to K2x2. If we solve this equation, we'll get something along the lines of like x1 is like, what was it? K2 x over K1 plus K2. I'll leave the solution of the equations as an exercise to the reader, but you will get that K1 x1 equals K2 x2 and equals K1 K2 over K1 plus K2 times x. And so this is our effective spring constant because this is equal to our spring force. And this is our total extension. So our effective spring constant in this case, K1, K2 over K1 plus K2. Now, what about the case for the pulleys? We'll have the same thing here, except when we pull this by a distance x, well, this side will get longer by x, and this side will also get longer by x. So we'll also have K1 x1 plus K2 x2 equal, K1 x1 equals K2 x2. But then we'll have x1 plus x2 equals 2x. So now if we try solving this equation, it will be similar, except we'll get an effective spring constant that is 4 times the spring constant if they were in parallel. So this is KB. So now we have to rank them. And to do this, this is sort of like, I guess, AM-HM inequality, but KA is greater than KB, actually. You can prove that this is always true. And these two are both obviously greater than KC. So this is our answer. Okay. We are a bit out of time, so I'll briefly go through the last three. Number 23 is a question about parallax. So what's going on here is the astronomer is on Earth, and the astronomer is orbiting the sun because the astronomer is on Earth and Earth is orbiting the sun. And this orbital distance is L sun symbol. Okay, but the astronomer observes this distant galaxy that's or a distant star. So the astronomer observes a distant star that's LS away from the sun. And as the astronomer orbits, this angle will gradually change from theta to 0 if the astronomer is here, and then all the way on the other side, it'll change to negative theta. So, and the problem gives that this difference, so the difference in these angles will be 2 theta, and that's equal to 0.5 arc seconds. And an arc second is just 1/3600 degrees. Okay, so what the question is asking is, what is this ratio LS divided by L sun? What is LS over L sun? Well, if we look at this triangle here, this ratio is just 1/tangent of our angle here. And we already know our angle, so we can just plug this in. And we should get a ratio of approximately 8 times 10 to the 5th. And that will be our answer. Okay. Let's briefly talk about number 24, which is we have a very heavy plate that's moving either upwards or downwards. And it randomly, okay, not randomly, it just switches velocity every t seconds, right? So at a random time, we have a ball that's dropped very far away, and it's dropped onto this plate. So what happens after the ball bounces off the plate? Well, the idea here is that in elastic collisions, the relative velocity will stay the same. So if we think about what happens when the plate's moving up, the relative velocity is, let's say, V final plus V, or what should I call it? Let's say I guess this is a bad name. The initial velocity of the ball, V0, let's call it V0. So the relative velocity of V is V0 plus V. So the final velocity of the ball must be V0 plus 2V, because it's V0 plus V relative to the plate, which we have to add another V. And similarly, if we drop it on a plate moving downwards, its relative velocity is v0 minus v. And so after it bounces back, its final velocity will be v0 minus 2v. So the question here is it more likely to increase in speed or decrease in speed? So the answer here is actually it's slightly more likely to increase in speed. Well, here's the reason why. So let's say the plate moves between here and here. If the plate's moving upwards while the ball first reaches this location, then no matter what, the ball's going to collide with the plate while it's moving upwards, and the ball will increase in speed. That's this case here. But if the ball enters this region while the plate is moving downwards, there's a small chance that the plate reaches the bottom before the ball, and then it'll switch its velocity and move upwards. So the answer is that ball is more likely to speed up. Okay, that's number 24. And let's go to number 25 really quickly. Although this is a bit of a long problem. So what to do here? What this problem is saying is we have a skier here, which initially skis down 150 meters along a ramp angled 30 degrees. And then the skier goes off a horizontal ramp with height 5 meters. So we want to find the horizontal distance of the skier once the skier lands. So we want this horizontal distance here. So first of all, once the skier enters the ramp, by conservation of energy, its velocity is root 2 GD sine theta. And this is just root GD, right? And from there, it's going to travel some horizontal distance, which is equal to VT. So we want to find T, which is how long the skier is in the air. So to find this height, it would be easier for us to shift in a frame where the incline is horizontal. So this is our incline, and our ramps here, 5 meters. Oops. Wait, I think I might have drawn the diagram wrong. Okay, so 5 meters is actually this distance, 5 meters. Okay. Now that that's done, we can find the time for this. So remember our frame's rotated, so we're going to have gravity at a slight angle. This is 30 degrees. So the effective gravity in the y direction is g times cosine 30 degrees. And the skier is launched from this point and has velocity v that we calculated earlier. So And also we know the height, which will be 5 cosine 30. So we can find the time by first finding the change in velocity. So we can use one of the kinematic equations, v final squared equals v initial squared plus 2 times acceleration times distance. And this will just be v sine theta squared plus 2, acceleration is g cosine 30. And the distance it travels is 5 meters downwards. So this will be 5 cosine 30 downwards. V squared and sine theta should be 1/2 v squared over 4, and d times g, and then 2 cosine squared 30, 3/2. So we can find its final velocity, and then we'll get the time by just, this is its change in velocity. So this is its change in velocity divided by the g cosine theta. That's its acceleration. We should get the time. And then after that, we can multiply it by our initial velocity all the way back up here to get the distance. And the distance will be 181 meters. And so that's our answer. All right, and that is the last question. So thank you everyone for listening. I hope you learned how to do some of the problems. And I'll see you later.